Okay, sorry about the delay. So, one more. Okay, so sorry about the delay. So Vesna Mitrovic is at Brown, and she's an NMR expert. She's going to tell us about NMR. Thank you.
Thank you. So it's a little bit of a shifting of the gears here. If I was a chemist, I have a lot of problems with chemists because, apparently the only thing you can do is tell structure with NMR. So they usually hate our proposals or any work we do. So, you have to make sure you never get the chemist referee for this kind of work. But my job, I guess I'm the first one in a set of talks here where we're going to shift gears. Now we learned in 2 days how to make, learn at least heard about what people have to go through in order to make materials and how difficult it is to guess. And I'll be the first one, I guess, to start this series of talks where, what is it that we do in order to actually know that what was made and synthesized actually has the property of what we think they should, and how can we use this? And so I hate myself for repeating this, but I guess everybody knows what this is, MRI. This is basically a third Nobel Prize that was awarded number 3 for NMR spectrometer, so used for medical imaging. We actually use the same thing, except smaller scale, of course. I don't put anything live in my magnets. That's a rule. Don't want to deal with it. And of course, this was the word nuclear was taken out for convenience, so people don't freak out. There's nothing radioactive, right, in the medical imaging, but in MRI imaging, so magnetic resonance imaging. And these pretty colors that you see here on this head, these are basically just, as you will hopefully know by the end of the talk, different relaxation processes in the brain, so they can actually separate which, not necessarily what the chemical element it is, but also where it's bound. So we heard in the last talk that somebody doesn't like to use, Wei doesn't like to use lanthanum, or right, it was lanthanum or gold and silver, but the lanthanum is lithium, sorry, it was a lithium, right? Doesn't show in X-rays. Oh, it's a favorite nuclear for NMR. You can do all sorts of things, and so this is what it shows here. So why use NMR spectroscopy? It's a kind of an oxymoron. It's a local bulk probe, meaning you get the information for every single nuclei. Just once it's cooked, once the JP gives me a sample, it's God given. That's where it is, and it will tell you information about that particular local point in the lattice. The problem, of course, is that you get the signal out of all the nuclei in a sample. So that's a problem, right? Because then you have to kind of think about it, how to interpret that. As one of my postdocs actually just recently coined the term, he's a theorist. You will see why I need a theorist. It's basically, imagine you have an NV diamond. I don't know if you've heard about magnetometry, right? It's very popular, it's great, So imagine that you actually, and it's really hard. In order to be able to do a true quantum measurement of something, you would love to have these two diamond NV magnetometers entangled. And that's, very difficult to do. I don't know if anybody has actually done it in a controllable way. And so imagine NMR is basically, Avogadro number of NV magnetometers. Okay. Of course, there's a price to pay for that. I'll come to that later. The good thing is that you can perform it in a very small samples. So 1 milligram is enough. You don't need a huge single crystal. There are really tiny crystals that are, sub-micron size, and we can, if you make your coil, we'll see later why you need a coil, you can actually deal with it. So that's a good thing, or bad thing, because your measurement lasts a long time. You get the very, very poor signal to noise ratio. Now, and the way you normally do detection in NMR, standard NMR, there are new ways is that it's inductively detected, so basically no contacts. So you don't have to worry about whether you have to put the contacts in the sample. And it actually probes, the nuclear frequency is about 0 relative compared to electrons, right? It's 2,000 times smaller Zeeman energy than electronic energy. So you're truly probing processes at zero, meaning ground states of your system. You know, zero, a micro electrovolt energy scale. So ground state probe by construction, right? Excitations, you don't see that. We leave this to neutrons, next up, right? And you have partial information about the Q vector. You can't control that. That's controlled by a crystal structure, by nature, again, the way your sensor is formed, right? And of course, because you're dealing with such a tiny samples, no contacts, you can actually perform it at extreme conditions, whether it's, you know, dilution fridge temperatures, high fields, high pressure. All of that comes with a cost, right? It's not trivial, but it's feasible. So how does this work? Quantum mechanics 101. Well, this here is a picture of what I'm showing you is energy levels of the nuclear spin. And you see the little sign here says I equals to 3/2. So I is the label for the nuclear spin, not to be confused with S and mix it up with electronic spin. Just, it's the same thing as S. You're in a zero magnetic field. Of course, you have these degenerate energy levels. And when you put in a magnetic field, you basically Zeeman split these levels. 3/2 is actually very useful because lithium is 3/2 copper. So, you know, we deal with this stuff quite often in the materials. And what one actually does, of course, once you have these levels that are split by this frequency here, the frequency of the splitting of these levels is given by the following here. Gyromagnetic ratio, you got to give a number property of the nuclear. So unless, you know, material undergoes nuclear decay, this is known to super high precision, less than, I mean, better than parts per million. And then H bar, of course, you don't mess with that. You know what that is. And then the local magnetic field. And what I mean by that is literally magnetic field that this nucleus feels at its site. So it could be everything, an electron passing by, you know, anything that you can imagine that would create a magnetic field, you know, orbital electron circling around gives you this field. Okay, so it's not just, you know, a magnet that you apply, but this is really the most sensitive way to measure magnetic field. There's nothing more sensitive because of the, you see H bar here, this gyromagnetic ratio is also, again, 2,000 times smaller than the one of the electrons. So there's just no, there's nothing you can construct as a sensor that would allow you to measure magnetic field with a higher precision than this. And so what we actually try to do here is to measure, right, this frequency. Usually when you have some levels, whatever spectroscopy is, you shine some excitations and then you look at the absorption of this. And then from, you know, NMR, from this absorption, what we can do is get the information about its local fields. Okay. Now, how is this done? So you put it in a magnetic field that creates this, splits this degeneracy. Now, you know, I need to, right, excite that. We need to absorb my, I need to send the radiation. Somehow I need to mess up, right? These, I have to excite the nucleotides from the ground state. Let's just go here, very simple picture. From the ground state, I have to excite them to the excited state. So I have to actually flip the nuclear spin, right? From being parallel to anti-parallel to magnetic field. So how do you do this on a paper? I have some formulas here. I love to write them so that you can actually, if you have an exam in quantum mechanics, okay? How do you change the orientation of the spin from up to down? What do you have to do? Anybody? I know this is supposed to be experimentalist school, but still. What do you have at your disposal mathematically? You have a spin, and then, you know, in quantum mechanics, when you want to achieve something, you need to apply an operator. Operator operates and does what you want. So what's the operator that allows you to change?
Rotation operator. I don't know what to do.
Goes up and down, spin up and down operators, right? Letter operators of the spin, just like the quantum. So you see these guys here. Well, it's I'm having H instead of, you know, spin is the same thing as magnetic field, but I have raising and lowering operators. And if you actually, you know, I guess everybody passed the fall exam, so doesn't remember this. So if you actually look back into your book, you know, the spin raising and lowering operators, they are linear superposition of X and Y. spin numbers, right? I can only know one of orientation. I cannot know the other two. So it's a linear superposition. It's a mess, right? I could never measure the other two. So the reason why I'm telling you this is that if you're about to design an experiment, right, and you want to flip this, you need to create these operators, okay? Right? And remember, quantum mechanics was made from experiments, right? So, you know, now I want to flip the spin. I need to create this operator. So I need to create a magnetic field, right? Which is the same thing as a spin that actually fluctuates at the right frequency to, you know, you need to conserve the energy, but it has to be perpendicular to the oriented to the my z direction, the magnetic field, right? So how do you create the magnetic field that you know that it's along, you know, in a plane perpendicular to the applied field in the lab? I don't like the equations, you know, E and M, that's too many integrals. Quantum mechanics is easy, up, you know, plus or minus. So you make a solenoid, right? And the field in the solenoid is always, you know, is along the axis of the solenoid. And this is why, you know, that big, if anybody had MRI, but this is why I have this sketch here, is that you see, this is my magnet in the lab, the big thing. This is the field that actually orients my spins. And then what you actually do is you make a solenoid, you know, just wrap the coil around your sample, your crystal, okay? Now, if you have a submicron crystals, they've been sometimes 2 weeks it took me to, you know, wrap the coil around it under the microscope. So it can be challenging sometimes. And the solenoid creates a magnetic field, right, along these perpendicular to, along the axis of the solenoid. So you just have to orient it the right way. And then you have everything. And, you know, you send the AC current, it would create this magnetic field that would then excite your spins. Okay? So, you know, you can actually excite them like this and then look for, you know, what happens when they relax back. When they relax back, think of it, you have this solenoid around your sample, just like I do now. If my spins are now going back to equilibrium, spins are little magnets. What happens when I change a magnetic field along the axis of the solenoid? I guess that's Faraday's law, right? It creates the change of the magnetic field, meaning the projection of the spin along the axis of the solenoid. That creates current. That's what we detect. This current is, yes, you know, sub-nanovolts, but, you know, with the right instrumentation, you can still, right? You just need the locking, and you detect that. And as a matter of fact, now, I'll stop the theory, but this is really what happens. One actually sends a pulse. Jargon is called pi/2, meaning I literally would, if you think that this is all the orientation of a nuclear spin, I put them all in a plane perpendicular to, you can flip them if you want all the way down. This is something we can actually control, okay, in the lab by how much. And these, you know, spins relax, they go back to equilibrium or just decohere because of the noise of the environment and so on and so forth. And what happens, imagine I put all my nuclear spins in the plane, which is perpendicular to my coil. They start dephasing, right? Every spin moves with a slightly different frequency because the local field that they feel is different. And eventually they're gonna, you know, if you think about the projection of these spins along your solenoid, you know, this would become zero. That change actually creates this signal, see? This signal goes under the jargon of pre-induction decay. You perform a Fourier transform of this and you obtain, you know, spectrum, right? As you can see, this spectrum here has a finite width. The peak is always, you know, some local field, but it's a histogram of all the local fields in your sample, really. That's what it is. Okay. Now, if you like the right equations, there it is. You will appreciate later why these equations are so useful, these quantum operators, because if you just want to get the structure, you don't need this. If you want to get into physics and what the electrons are doing and actually look, how do I say, not just, you know, we don't really care what the local magnetic field is. What we care is what is electronic susceptibility, electronic response function. That requires a little more tricks, right? And these are very, again, for those of you who are mathematically inclined, this is how you would actually write this pre-induction decay signal. It's a trace of, it's an ensemble of the nuclei, so I can't treat them as spins. You have to use the density matrix. Formalism, this is the direction of the applied field. That's a nuclear spin, and then there's some kind of arbitrary decay. Again, you can sum up of all these eigenstates of the nuclear spins, but I'll come back to that later. I just want to show you that we actually know how to write this mathematically. Normally we don't do that, but you'll see why this is useful. For people using quantum computing or even NV magnetometry, actually this is a picture basically of this that I just copied from Qtip. It's one of the, I don't know if any of you have heard of this, but it's a very popular software for education, for basically quantum gates, all the sorts of quantum operations that you can simulate. And this is their picture actually from there that it will allow you to use a block sphere, right, to represent spin states and so on and so forth. But it's basically at the end, it's nothing else but the induction decay that we've been measuring for last, I don't know, NMR was discovered in end of the Second World War. Okay,
So, one question, what the S of T is just a
signal.
okay.
Yeah,
function.
yeah,
Right.
And I is always a nuclear spin, and every what?
The left graph, right? Yeah.
Yeah, the left graph. That's a mathematical expression. Yeah,
Thank you.
yeah, and when you have a nuclear spin, right? I mean, any spin, right? 1/2 or higher, it doesn't really matter. But this is how in today's world we love to represent this. This is been in NMR world forever. But this is this famous block sphere that represents the qubit, right? And if your arrow points up, that's your up state, right? So this is my spin up. This is spin down. Old-fashioned spin up and spin down states. The phase, right? Again, we have this pulse, right? That we can control the duration of it. And because it's a very short and very strong, it actually coherently affects all the nuclei, right? And so you can really control, by changing time of this pulse. So I think somebody mentioned earlier, you can actually control the phase of these spins alter. And this is just a modern or people from QS, quantum information science, representation of what has been done in NMR forever. And this is if you look at quantum gate, is basically you start somewhere here and then you apply time evolution operator U, and then you get your result. Well, that U is our pulse. Okay, that's what it is. You can control it with a very, very high precision. And so there's something very useful actually that we can also do. FID is quite problematic because this pulse here that I talk about pi/2, we're talking typically in the lab. This is something that lasts about on a time scales of microseconds. Now, if you're in chemistry and you're doing structures, it's milliseconds just because they deal with liquids. But for us, even if you have magnetic materials, you want to be as fast as you can. You would love to go into nanoseconds, but unfortunately, some technical issues there. And so, microsecond time scale typically, and it's a kilowatt of power that you send it, right? But it's a very tiny duty cycle because it's so short. And so, your whole electronics is kind of, to use a jargon, ringing, right? So there's a dead time typically of several microseconds, which actually, there's a dead time in the sense that your coil has to recover before you can detect. It rings, acoustic kind of ring down. And sometimes, depending on what you're trying to probe, we can actually, this could be very important information about some, fast time scale processes. So you don't want to miss that. So basically, the way around that is to actually generate an echo. And this is how the echo, my animation already started. Well, it will go back. So this is how it works. You actually put the spins, you apply this pi/2 pulse, meaning you put it into XY plane, perpendicular to the applied field. Each one of them will be phased, runs, moves with a different speed. Okay, just because it feels a different local fields, local fluctuations. And then, after a certain time tau, okay, you see this time here, they call it t, between the pulses, you actually apply 180 pulse. So I'm talking an NMR jargon, but 180 pulse, right? You invert in your world of crystals making, I can actually invert the axis of time. That's exactly what this pulse does, right? It's an inversion symmetry pulse. And so it's basically, you literally reverse the axis of time. So if the nucleus was going faster, now it goes slower, right? And they would all focus, again, after this time t, you see they will all come into, if you look at these arrows, they will all come into the focus and create this echo, the peak. So this way I cheat in the sense that I don't have to worry about my dead time of my electronics, and I can get the information about the beginning of time, right? The peak of the echo is the zero of our time evolution when we started measuring and so on. Okay.
Sorry, and the time that you have to wait between the pi/2 and pi pulse can be anything, or?
No, it cannot be anything. It all depends on how fast these spins dephase, right? So it has to be something, there are things that you cannot rephase, so that you're rephasing, it depends whether, how they interact, whether, there's, time inversion symmetry affect this or not. So this is what it comes on. And so this is how this is done in the lab, just to, since experimental school, I wrote too many equations. But this is basically what one does, is that you have this radio frequency pulse generator here, power amplifier. So these pulses are very tricky, right? So you actually have to create the whole sequence of them. They allow you to invert the axis of time and so on and so forth. So there are quite fancy sequences that one can create depending on what you're actually trying to probe. So you do that with these, fancy machines, RF pulse generators. Then you have to amplify this. All of that goes into your resonant circuit, right? So the reason why you have to have this resonant LRC circuit, your solenoid is an inductor. It sits, that's where L is an inductor. That's the coil, that's where your sample sits in. Of course, there are losses everywhere because, you did a bad solder joint, so I need my resistance there. There are these capacitors here tuning in, meaning it allows you to tune to the right frequency. There's another one, says it has a substrate, N stands for matching. You actually have to match everything to 50 ohm again to minimize the losses. Okay. Back in the day, before cell phones, we had to make all of this by hands, but nowadays, that's exactly what your cell phones use. Slightly different frequency, but you can actually, at least we have our network analyzers that can actually, test the matching, and you didn't have to make your own things, that you have to do today. And so, we have this traffic controller here because, as I said, you have these kilowatt powers going into your probe, into your resonant circuit, and then, within microseconds, you want all of this to recover, and you want to be able to detect the signal, and signal comes here. Blue is cold, meaning non-volt signal goes to preamplifier, spectrometer, blah blah, for the analysis. And there is actually this traffic controller is a very interesting. I like to call it quantum device, even though it's again, thank you cell phones for being able to actually have this. It's an actually quite interesting wave guide that is generated so that it controls by the length, right? So electromagnetic waves are, and you can control the interference just by these strip lines, the way they design them. And so you can control what comes, the signal comes in, and you have two ports. One is same signal, the other one is 90 degrees out of phase. And you can put them back to back, and you can actually rearrange where you want to get constructive interference and where you want to get constructive and destructive. And so you arrange it in such a way that this signal, once it gets into the probe, it actually completely destructively interferes into this blue line here, and vice versa. It's quite amazing, the power of interference. There's nothing, there's no leakage there. This is not, your DC signal that can leak noise and stuff. It's quite impressive. that it actually works. Well, and this is basically how this schematic looks like in the lab. So a big magnet, and I'm just showing you here the solenoid, the cryostat, so we want to cool down, and this is the long probe. And the reason why it's so long is just that you want to be able to sit in the center of this magnet. And this is how your probe looks like. So all the electronics for these capacitors are here that we can keep, because if you go to some chemistry lab, Bruker spectrometer, they basically, you just want to get the structure very quickly. Every experiment I touch is months before we figure out. This is 20 minutes you go, you push the button, and there are basically 3 or 4 elements depending on how much money. It's all optimized. You tune, you switch some box, and then it allows you to probe usually carbon, proton, and phosphorus, nitrogen, whatever, depending on how much money you pay Bruker. Since we never know who's going to give us material and what nucleus we're going to study. So you want to be able to actually tune the frequency, match, you want to change the magnetic field so that you can study physical properties and functional field. And so this is all homemade. Goniometers you can rotate, right? So you can look at the anisotropy as a function of applied field. The little antenna, which is nothing else but the loop of 50 ohm resistor, because you match everything, and so on. And as you can see, all of this can be quite tiny. And this is if you want to be really good, you put this metal to shield the noise from outside. We don't have radios anymore, so we don't have to worry about this. The classic AFM band, that was very painful 20 years ago. So now let me go back to tell you what is it that we want to probe. So the simplest thing is to look at what's called a static measurement, right? So we want to know, right, what creates this local field. Okay, so this is just an example of some crystal. I usually refer to them as just crystals. I don't really care what formula they have. And so just showing you here, for example, you have these cesium atoms. This is cesium NMR. And you see the different shades of these colors that just kind of tell you where they show up in the spectrum in a different location. And there's many more things if you were trying to actually look at the molecular structure. Me as a physicist, this is the only formula I care about. What creates a local field is what I apply, plus this thing here, which is actually a hyperfine field. Hyperfine interaction is it's an overlap of the wave functions, really, of the nuclei with the electronic wave function. And it doesn't have to be direct. There's contact. It could actually, if you have magnetic material and have very complicated transfer orbitals that transfer the magnetic interaction J, then it has this transfer hyperfine that goes, and again, there's as long as there's an overlap of quantum mechanical wave functions, somehow it gets to into the nuclei, you can sense it. And it turns out that in most of the materials that we study, this is really the dominant interaction. Everything else can be tossed away. It's a minor perturbation problem. And so this hyperfine tensor here, this is like 3x3 tensor. It allows you to really see a lot of things, but again, it's you need to bug your first principle calculation friends to, and it's really tough to calculate. So you measure it. There are ways of doing that. That's the easiest thing to do. And what is important that what creates this hyperfine field is actually, as you can see, just this tensor. It's given by, once you cook the crystal or a powder, it doesn't really matter. That's what it is, and we can measure it. But the important thing is that the field is created by this, which is electronic spin operator, right? So that is, I actually write this correctly. I average it typically, so it's a electronic spin, which is projected along the applied field, right? So quantum mechanics takes care of it. This is the only thing that I see. And if you're actually trying to be very careful, you should actually now, you have to think about it. This is not an instantaneous quantity, right? Especially in quantum materials, don't forget about quantum fluctuations, or thermal fluctuations for that matter. And so you have to be honest that you have to remember that you're actually averaging this over this time of your echo. So typically, 10 microseconds. If it's longer, it's longer. The time between the two pulses when I invert my axis of time. And so that's what you're probing. Now, if you talk to your theory friends, you can actually figure out that this quantity here, electronic spin, the experimental is called that, right? Susceptibility, right? So this is actually gives you a direct measure, this local field, right? Direct measure of the magnetic susceptibility per site, right? Because you're measuring per nuclei here. And then there's something that you probably heard. People talk about night shift, right? And the shift is the following. So, you see this omega zero is basically this term here. So it's this constant times the field that I applied. So imagine if your nucleus was just feeling no other nuclei or no electrons. So in the vacuum, you put it in a magnetic field that you apply. That would give you, this term here, omega zero. So it's a vacuum in, NMR language. This is our vacuum. So each nuclei has its own vacuum frequency here. If there would be no interaction. And so what we actually do is we always plot what we measure, the frequency that you measure of your, whatever signal, whatever you're studying, minus this vacuum, you divide by that. So it's in, unitless, right? And that's a direct measure. That shift is a direct measure basically of this, susceptibility. If you notice, I want to be very careful here. This is static, so it's Q equals to 0, and also at frequency. So if you think about in terms of electronic response function, this is Q equals 0 and omega in energy, omega 0. So this omega here refers to electrons. I apologize for shifting because, between the two. And, these arrows here, so only on my first slides, the arrows were denoting nuclear spins. Right now, every time you see an arrow is an electron because everything else is just a minor perturbation to the story, okay? So imagine I have a ferromagnet, right? Everybody knows how that looks like. Then, this is your vacuum frequency, and then you have this shift, right? And the shift is proportional to this moment of the ferromagnet. If you have an antiferromagnet, you see you get two lines. One is shifted to negative or positive relative to the 0. If you have incommensurate modulations, this is how the spectrum would look like. Now, the reason why I know this is basically, you arrange your spins and then you just calculate the histogram, meaning the probability distribution of that. And this is how you get these pictures, okay? And in the metal, just to remind you, if you ever took complicated classes, solid state, whatever, anybody theory, that response function, that susceptibility, if there are no interactions with simple Fermi liquid, that thing is actually in a Fermi liquid that's just proportional to the density of states at the Fermi level, okay? So the night shift actually is a probe of the density of states if you're talking about, Fermi liquids, okay? No magnetic states, okay? So I want to show you some of my favorite, which is very complicated one. So this not just these simple magnetic structures, textbook examples, but you can resolve something very interesting, and that is this is every experiment that was done on this material, it doesn't really matter what it is exactly, was that they found a very tiny moment. Now you do the chemistry and you count, and you're supposed to have some huge moment, and there's the problem of the missing problem of the fact that when you do magnetization, you do muons, you find these really tiny moments. And we were able to actually figure this out with NMR. And so if you think about it, we did this sodium NMR. You see this yellow nucleus here and yellow. And then these arrows are showing you orientation of these magnetic moments of osmium, whatever it is. Well, we measure the spectra. We rotate the magnetic field and you do all these complicated measurements, and then you go to your computer and you actually, your spectrum is basically a histogram of these internal magnetic fields. And for each nucleus, this is what this nucleus feels. See this is a unit vector along the direction of the applied field, which I know it's my big magnet, I know which direction that is, right? And then you sum over all these nearest neighbors. You see there are 6 of them, right? hyperfine tensor, and then these are the moments, magnetic moments. So you can actually, you treat it almost, so you generate the spectrum. The spectrum that you measure is basically probability distribution of this. So you let your computer calculate all these arrangements, you fit your data to, and then what you actually see is that, yes, you have these moments that are, 0.6 Bohr magneton, I remember this, and you see you have a plane in which they all are oriented along this direction A, and you have a different plane here, they're pointing along the B direction, so they're staggered, or this like almost 80 degrees away. And so, if you think about it, every other experiment measures the projection along the field, along this easy axis, which just turned out to be whatever, 110 here. And so, because they're staggered so much, this is why you actually cancels, right? So if you do any bulk measurement, you find these very tiny moments. And there's something really interesting is that if you look at this tensor here, normally it's diagonal. In this particular messy material, there are these really complicated orbital orders, complicated transfer exchange paths. And just by fitting, this is what we find. So you find basically this hyperfine tensor has no symmetry. It's a mess because of this. But it's a good thing because it allows you to actually probe the complexity of all these orbitals, even though you're not, you're not doing like scattering experiment where you can trust and say, hey, this is how they arrange, right? It turns out that these orbitals involved a lot of hybridization with oxygen, so you can't really do a scattering experiment on it, but
So what is the material there?
it's double perovskite, sodium, barium, osmium. I'll show you the formula.
Okay.
To measure this tensor, you have to do measurements in different directions.
You rotate the magnetic field, so you have to do different
So you
planes.
sample without rotating, you rotate magnetic field.
No,
and
you would
you
never.
also-
You need to do the full rotation of the different planes, even depending on how complicated it is. Yeah. So it's a lot of measurements. It's not easy and a lot of simulation afterwards, but it's still.
And the off-diagonal terms you also get just by rotating them.
There are tricks to measure off diagonal terms. Yes, exactly. They contribute because of the complexity of the way that I can manipulate the spin, and I can control it, how long it evolves in the XY plane. It actually picks up off diagonal terms of the tensor. It picks up that information again, depending on how you arrange the sequence.
Okay.
All sequences, so you can get that information.
So changing the times in your measurement.
Yes, playing with this stuff. And
Sorry.
Yeah.
So the message in the previous slide is that you can refine this spin structure in a
Yes.
complicated system that normally via bulk probe like susceptibility, you would never see in the or
exactly,
would average out.
or So even though it's a bulk probe, there are tricks that you can play because of the, the fact that you can play with these pulses and get the phase, these, you can get these off diagonal information of these tensors. Actually, again, if you ever in your book back in quantum mechanics, well, it depends which book you used, but the off diagonal terms are the coherence terms. It's exactly what involves these T2, so you can actually pick it up, in a density matrix, So that's the beauty of it, In principle, right, it probes density of states, it probes the magnetization, just like squid, except that you have this extra information. Not easy to there, but if you do that for a living, then
I have a misunderstanding or help you out from my understanding. So you have a solenoid on the sample, and then Faraday's law, you measure the small current because of the spin through, and then so how does that become a localized measurement?
it's localized because you get that information from, first of all, you excite all the spins, you put them all into coherently, right? And each nucleus gives you its own, so the spectrum that if I look at the detail of the shape of the spectrum, it's a histogram, So yes, it's a bulk probe. I get information of as many nuclei as I have in my sample, but each one gives you an information about, its own local field. So it's, it's a little bit of an oxymoron. It's a local, but it's
So it's like frequency dependent.
yes, usually. And also because I can use these pulses and manipulate things coherently, it's also, phase dependent, time dependent, right? That's an extra information which is not easy to restart. But I don't have a lot of time. I just want to also tell you, I started with 3 halves. So lithium, copper, very useful stuff, right? Sodium. So if the nucleus actually has a spin higher than 1/2, actually it's a wave function. Like, okay, you have to be a nuclear physicist. So who cares? The point is, look, it looks like this. It's not nuclei is not the circular thing, but it's elongated. And so it actually has, this quadrupolar moment, right? So it's like a cigar, right? So you see. And it turns out that every time you have a nuclear spin, which is higher than 1/2, you have this quadrupolar moment. And then, it's actually even in the separated book in quantum mechanics. If you have these quadrupolar moments, well, you can use something, Wigner criteria, and you can look at these. So basically, this nucleus actually, if it's in a local environment where there are electrical field gradients. So now I'm talking about electrons again, right? And if you have an electrical field gradient, that gradient interacts with this quadrupolar moment of the nuclei. There's actually a problem in Sakurai's book of quantum mechanics of that, and it's like takes you 5 pages of paper to actually show that these electronic orbitals, you do all this math just to show that at the end, look, this Hamiltonian actually converts into this. This looks like a Zeeman Hamiltonian, except that the spin, right? Zeeman is just the spin times the field. You see, this is some field, okay, whatever this is, right? Nuclear property. And then the square of the spin number, okay? So it's actually very useful because you see, this is a square now in a spin number. So if JP comes to me and tells me, hey, I cooked this new material and really, I don't know, there's charge density weighting, there's magnetic fluctuation and so on and so forth. And I would love to know what causes this superconducting state. Is it charge fluctuations or is it magnetic fluctuations, right? We would love to know which one. This Hamiltonian has a completely different symmetry. It has its inversions, right? It's square. And you can play again with the pulse sequences in a time evolution and separate what is magnetic, what is quadratic, if you're lucky, okay? Again, if the time scales of the things are right. And that's really a beauty of this, having this quadrupolar interaction. Now, if you're a chemist, they'll never want to touch these nuclei because this doesn't allow you to do very high precision, spectroscopic measurements. We love it because it just gives me ways of separating the two. And it actually, because this Hamiltonian looks like Zeeman, right? It's the same physics, if you diagonalize it, you get these levels. So this is Zeeman plus this, and EFG stands for electrical field gradient. And I'm talking, this is created by electrons, right? So it's a way of actually telling you about electronic orbitals, right? Not spin of electrons, but charge, right? And if you don't have this electrical field, so for example, it's a little complicated also that if you have a cubic symmetry, then there's no electrical field gradients. So if you have these perfect crystals that are cubic, this electrical field gradient would always be 0. So no splitting from that. If you break that cubic symmetry, then you start actually developing these electrical field gradients. Okay. And I have this notion of qubits because that's what, people actually use this electrical field gradients in crystals to actually do some simple simulations of, qubit gates and so on and so forth, evolutions. Just get the crystal like a sodium chloride or something like some salt that you can apparently cook very quickly. And then you can have 2 qubit gates and you can demonstrate C-naughts and so on. It's these electrical field gradients that give you qubits, right? Quotation mark. But if you actually, again, analyze these Hamiltonian and, it can be written, the long story short is that my splitting of these peaks, also how they, as you rotate the magnetic field, you see, this is the principal axis of these quadrupolar moment of the nuclei, or sorry, BZZ is the principal axis of electrical field gradient. And if you rotate the applied field, the different planes of the crystal, you actually can, by just looking at the splitting of between these peaks, of course, the shape as well, you can actually figure out exactly what this electrical field gradient is. And it's a tensor, so you can know the principal axis. So you can actually figure out the local distortions of these electronic orbitals by doing that. And again, if you do the full rotations in different planes of the crystal, that's what I'm actually showing here. You can work out the math. Again, you can find information about the full anisotropy of these tensors and so on and so forth. And this is an example where we were able, again, same material, the complicated one, this orbital order. We actually know exactly that it's orthonormic just from, again, studying these rotations and so on. And these are pretty pictures that we were able to recover actually afterwards. You can also do a lot of dynamical measurements. This is very useful, and there's something that goes by name T2. So it's a decoherence time. So how quickly my spins decohere. If it's probing everything, in this process of decoherence, there's no energy exchange. So it's really tough to calculate, but it probes, fluctuations of the field which are parallel to the applied field. That doesn't change the energy of the system at all. You can also measure something that goes by the name of spin lattice relaxation time. How long does it take for my nuclear spins to go back to equilibrium? If they were in vacuum, they would never relax back. So the relaxation process is actually controlled by their interaction with electrons. Gives us basically, in terms of response function, if you think about materials, this is the exact same quantity that is probed by neutrons, dynamical spin susceptibility by neutron scattering, except at omega 0, right? And this is your real part of the same quantity, again at omega equals to 0. And since I don't have a lot of time, if you're actually probing a simple metal, this is very important, this is square of the density of states. And it was recently a colleague of mine sent us, they didn't know whether they were, for example, doping this metal with electrons and holes, and they were not sure whether the dopants are going where they want, right? You're never sure. And we're talking, 4% doping levels and and so it was the first time actually in my life that I actually saw something that precise. Because usually, you have junk and nothing ever works. But it was amazing that we were actually measuring this T1. So the shift is the density of states. This is a square of the effect. And both shift and basically when we measure these relaxation rates, consistently show us that the density of states increased by 4% by these electron doping, which never happens, in real life. But it could actually be a quite helpful probe if you're probing some bands, right? And we don't know where it goes. So look at just a simple that just happened. If you have quantum wells, again, all these energy levels of a particle in a box, you can probe by this. And since I don't have a lot of time, I'm going to skip, but I'm going to talk about something which I think is very relevant. I told you we have a coil, and coil is great because I don't have to put the leads on my sample. But this is something that, doing experiments is very painful, and you can never trust the experiment because, you're measuring some very small effects. So I actually went to my theory colleague and I calculated this and showed that it's true. So we have a theory publication. But this is, so, there's a big issue about, so we can do resistively detected NMR, and I'll explain, but we actually want to look into this to actually be able to probe topological nature of conductive states. So, this is actually a photograph, a fancier version. This is generation 1, generation 2 of the same sample. So this was diselenate, cleaved and plopped the leads on. And then there is a surface coil, NMR coil, lithographically deposited, that's the fancy version of that. So that's the coil that I'm going to use to send the frequency. I have 4 leads, right? So doing resistance measurement. And the idea is the following. If the topological states, these surface states, right? If I have a topological insulator, we would have these chiral states, right? So you see these red spins are pointing down and blue, they're pointing up. I just copied this because I was lazy to make my own, right? So I have these chiral topologically protected states that conduct. And, the problem is that what gives us topological protection, right, is a spin orbit coupling. So if you ask me to, this is a spin up and down, great, we have these arrows, but in reality, spin orbit coupling makes you, right, it's not, spin is no longer a good quantum number. So, in a very simple picture, right, if because of this spin momentum locking that gives me this topological protected states, that also tells me that, electronic spin, right? Even though we draw it like up and down, these chiral states, it's not a good quantum number. So if I was to actually send a microwave, right, to flip this electronic spin, there is no resonance absorption because the spin is not a good quantum number. Spin is actually this mess here, okay? So there is no way. So the question is, if we're ever going to use this, right, when you device something, I mean, device means I can control up and down or two states, right? So I need to be able to maybe, you know, flip the spin, right, or get some kind of non-reciprocal process, not just conduct, right? Or, you know, if I want to, it's great that it conducts, right, because there's no resistivity in these states, but you have to write in information, right, that's disturbing the system. So how do you do this? And our idea was that, well, I can use the nuclear spins. And the way you can do that is that nuclear spin, okay, I was lazy to change the labels here, but they are coupled to electronic spins, okay? Whatever the material is, even here in the States, by these local hyperfine interaction. And the local nature of that interaction wins. So actually what happens that locally, that's a kind of in a hierarchy of quantum mechanical things, it's the first thing that happens. So if I have a nuclear spin and I actually flip it, right, and it's a nuclear spin, yeah, it's all over my sample, but there are the ones that are coupled to electrons that are near these states, topological states, chiral states. They will be, you know, I flip them all, and they will actually do nuclear spin would actually flip the, you know, simultaneous with electron because of this hyperfine coupling. You have to conserve the energy. So you flip the electronic spin, sorry, nuclear spin, there would be a simultaneous spin flip. Okay, so it's as if I have created, you know, spin scattering, like the impurities, right? But in a controlled way. And when this happens, because, you know, now my electron in this chiral state, right? It's in a blue, but if it flips the spin, it has to go into red, right? Because of spin momentum law. And so there will be a change in the resistance. And, you know, it only happens if you have these topological states. I mean, in a normal metal, you would never see that because it's, you know, there are all these states of other orientation that are not allowed there. So only if, you know, your conductive states that you're measuring are chiral or topological, you will actually have this, you know, signal. And this is something that we actually propose to use. So, you know, this is the theoretical picture of what I just said. But, you know, to control these kind of spin devices that have these huge spin persistent currents, and nuclear are the key to controlling that. So, you know, again, it doesn't matter that the electronic spin, you know, it's local. And that's the beauty of it. And this is actually just a data of this multi-selenite kind of, I don't trust it, I have to redo it. But the long story short is that, you know, there's some, you see the resistance that was measured on average, and you see this dip here was actually happening exactly when you were irradiating the nuclei with the frequency of the bismuth. And as a matter of fact, you see this is a bismuth spectrum here, and classic NMR, okay? This is a resistance that we measured, and if you actually compare it, the frequency shift is exactly, you know, that. So this width corresponds to the blue, so different samples, different doping levels, and so on. So we actually see these changes in resistance right at resonance of bismuth. Okay, I don't have a lot of time now, so I will, yeah, I will stop now and we'll talk later. But okay, there's too much anyway. So just wanted to show you how we can squeeze the NMR was used to test quantum computers. So, you know, my spin is a qubit and entanglement. And I just want to tell you one thing, that because of these pulses and control that we have, I really don't care about, you know, making a quantum computer, but this little picture, all the tricks that they developed, we're actually using now to get the entangled, well, you know, the response function in the materials, and there is actually making the progress in it. So it's quite interesting what you can do. So anyway, I'll stop here. Can you repeat the question, sir? Yeah. Yes. But you measure it, I mean, that's the whole point, so.
If there's more symmetry, lower the heavier one.
Not necessarily the symmetry, it also depends what the electrons are doing, right? So what is the ground state that the fluctuations, the nature of. I would say more than a crystal symmetry, what affects what phase, electronic phase you're in, correlated phase, yeah.
Question, yeah.
For the business alive device, it's like 14 Tesla and 4K. Was that with the max field and the lowest temperature you could? But I've seen 11.6, but you could go to lower field with the
The spectra were measured at 4 Kelvin. This measurement of resistance was done at 50 millikelvin. So you really have to, it was only the dilution fridge measurement. And no, it's just it was just a convenience where the probe was tuned. Yeah.
So a follow-up, sorry. What would limit that? Would that be the scattering and the bulk? Would be a better.
We were actually, the fields here were set by, because it was 3D crystal, so we just wanted to be in a quantum, I mean, you have to get into quantum limit to have the topological, so you have to make sure that you gapped the bulk states, and that's why the fields were chosen depending on, the content, the doping levels.
Here, who's first?
So your fields are really high. A lot of the samples in our lab leave the ground state like below 5 Tesla. So is there a low field analogy, or is the signal?
Yeah, you can do the same thing. You just, you just have to make a different coil and work at lower frequencies. Yeah. It's more convenient. You get more signal with the higher field. So if physics permits you, I mean, here we had to go to high field to get the bulk. So it really depends. You can do FQR in zero field. So.
Are there certain nuclei that, just as an experimentalist who doesn't do NMR, that I should think, oh, this might be good? Because I know that some just don't have any spin at all.
There's a table, and then you just look at the table with the sensitivities and stuff, yeah. And there's a list of, fortunately, quite a few are pretty good, yeah.
And isotopes as well.
You can exchange the isotopes, yeah. If anybody's in high disease, we used to do this insane oxygen exchange, so $10,000 per liter.
17.
Yeah.
Question here? No? Colin?
That's a really interesting result there with the resistively detected NMR. I just have a kind of an experimentalist devil's advocate question, which is, do we have to worry about any heating of the sample during pulsing?
Yeah, that's why, this is why I actually did not publish my experimental result, but we did write the theory, so we know how to test for heating. It's actually, this works. The easiest way to test it as a function of heating is to rotate the applied field, because it only works for the perpendicular directions. So if you rotate, you lose the signal. And it's just kind of a trick that was played back in the day for quantum wells, the probing physics of quantum Hall effect. So Zeeman versus, the gauge field. So you can basically, we're trying to repeat the experiments and deal with this problem. So there's, we've been doing pulse versus continuous wave varying but those are things you can actually verify. It's painful, but you can verify this, yeah.
So does in the case of business solenoid, there's bulk states that are getting away.
Yeah.
So if you have a true TI material, does that help you?
If you have a true
Bulk, gapped bulk states, truly gapped.
that helps you get a larger signal because, right, it's you detecting the conductivity, right, of your topological, but you also measure in bulk, and only the topological states will give you this change. So, you're measuring much smaller effect, right? So if you can fully gap them, then effect should be larger, right? And then the through kind of test for that is just to rotate the field.
Any other questions?
So in this experiment, you're applying a pi pulse to invert the nuclear spins, right?
Yeah.
And then you measure like these changes in resistance that you measure. How long do they persist? Are they like? Is it like it goes like T2, like after you?
Well, it does, but the resistance is like, we did not really look into that. We're just measuring instantaneously resistance while you pulse it, right? Because you don't have to worry about that time or anything because you're looking at your leads, right?
Yeah,
And you're pulsing, with your little coil. So, it's instantaneous. Or we didn't really look into, you have to find the effect first and then go into,
Yeah.
Next step would be to if you actually detect it, that it's not hitting anything else, is to actually play with the complicated pulse sequences to actually, create like the real gate, real device,
But would you expect it to persist until T2 or T1, for example?
T1 here,
T1.
yeah, because this change in resistance by T1 by actually flipping the electronic spin, yeah.
Okay. Here.
I have a structure question. Would you be able to probe like a substitution between gallium and germanium? And you can
Gallium.
the probe.
Yeah, gallium is very nice nucleus. Of course, it has 2 isotopes, so yeah. I guess the way I would do it on gallium and then look for, as you put germanium, what changes in gallium itself, right? Germanium has a very big signal. What?
Would you get like a nominal composition?
Supposedly, yes. Yeah.
Lauren?
You said you wrap your solenoid around your sample and have all your slides going that nice added
It doesn't matter, you just wrap it around it. It doesn't have to be a solenoid. As long as it's a loop, the field is, even if you screw up orientation, it's amazing how quantum mechanics is really simple. So selection rule tells you what you can spin flip, right? So even if you like completely misorient your coil or whatever, you lose the signal, but the point is that it's just the field component which is perpendicular to the applied field that matters. So, if your coil is a solenoid and you have a needle shape, you will be losing what's called, the field that you detect. You have to, the strength of that current is divided by the volume of your sample versus the volume of your solenoid. So you're losing signal, okay? But the exact shape does not matter at all because at the end of the day, you can always crank the power optimize it. It's what flips the spin, what gives you is the perpendicular component to the applied field. So you can be very forgiving in a way quantum mechanics tells you it's all or nothing. So you don't have to like really worry about the exact shape and so on and so forth. That would not distort what you see. You will lose the intense signal to noise, if you really screw up, but you will not lose the information,
Final quick question. I can come up with one of my silly ones. Earlier you mentioned AM and FM radio. Are there any instances of finding something that you think is really interesting and then figuring out, oh, it's NPR or the local classic rock station?
They're very powerful compared to what we probe, and you ground well your gas that you find would shield it. Yeah, or loops, in a spectrometer. If you it's so strong that you can, it just literally overpowers, so you can't even make a mistake.
Okay, thank you. We'll come back at 11:10.